So we are still, I would say from the class point of view, we are still warming up. So we are not into anything big yet, and slowly we'll move towards more interesting topics. So these are broad ideas we'll cover today. We'll start with examples of statistical models. We look into distributions, not all of them. It is not feasible to cover every statistical distribution that we use, but the key ones. We'll also do some simulation of random numbers and samples using R. So R is a very powerful package that can help to simulate data from various distributions very easily. And we'll also cover some of the model assumptions that we use when we build a simple model like simple linear regression model. So that's the plan. This is a small data that I'll use as an example. And this data is called roller. It's about lawn roller data, where we have different weights of a roller that were used for different parts of a lawn. And whatever depression was achieved is recorded. You have 10 pairs of data points. So obviously it is assumed that when the weight increases, depression is likely to increase, and we do see that kind of thing happening. Like with 1.9 we have 2, but when you go to 12.4 it's about 25. And you can also see through this scatter plot that there is a broadly like increasing trend. As weight increases, depression increases. So in the scatter plot, we use various terms to represent or call these variables. So usually x-axis variables are called independent variables, and y-axis variable is called a dependent variable. So that's a very common name you may have already come across. Sometimes x variables are also called predictors, and y variables similarly have other names like response or effect. So if x is a cause, then y is the effect of that cause. When we look at the scatter plot, we see it's not like perfect linear, but you can see that overall the pattern is increasing. As x goes up, y also goes up. So we can very easily use a simple linear regression model here and build a model and see how they are behaving. That's what is done in the first picture. So we have applied a simple linear regression model. So line of best fit shows this straight line pattern. But I have also added this plot here where you have a nonlinear pattern. And I achieved this by adding a quadratic term. So here you have y equals the intercept plus slope times x. So that's how we represent this equation. But when you have y equals intercept plus b1 times x, and then you add another term, maybe b2 x square, so you get this kind of pattern by including that quadratic term. And with a software like R, it's very easy to include x square, x cube, x4. There's no end to it. You just need to make a small change, and suddenly you have very complicated or very complex relation between two variables. But if I ask you which model we should prefer here? If you look at the two pictures, any idea what do you suggest? I have not included like x cube, x4, those terms. I try to keep it simpler.
um, methods and see which one has the highest R squared value.
So that is another way of looking at it. Like we can calculate r square and choose the one which gives us higher r square.
I think just intuitively, I'd go with the right one because it makes sense that if you keep adding weight, eventually you'll have diminishing returns on the depression.
That's right. Like if you keep on adding terms, your r square will continue to go up. So where do you stop? Some people suggest we should, like given other things constant or more or less equal, we should go with a model that is simpler. So if performance wise both situations are same, then go with the first one. Unless like second one gives you improvement on some aspects of the model, uh, if that happens, then probably go with the second one. But it's also true, more complex a model, more difficult it is to explain, and also it is more expensive. So any extra term in terms of like extra effort is going to be more expensive. But let's look at some more output. The intercept term comes from this line intercepting y-axis. So this line, if you extend to y-axis, it is going to cut y-axis somewhere here, and that's what is y-intercept, and it's about negative 2.087. The only reason you may notice is like if you extend it here and 0 is here, so it may look as if it's not going to negative 2, but note here this is like 2.5, then 5, 7.5. So there's some compression in x-axis, so that's why when you make it from 0 to 2.5, you will see that the line will cut at negative 2. And then slope of the line is 2.6. The interpretation of that is if weight increases by 1 unit, the response, which is depression here, so that is likely to change by about 2.7 units. So any unit change in weight is going to change response variable by 2.6. And you also see, apart from like other calculations, standard error, t-value, so all that is baked into p-value, the last column. And the last column says that if you see stars, that means the variable is statistically significant. And number of stars only indicate like what is the level of significance. So this is significant at 0.01. If you do 1 minus of this 0.005, so that's your confidence in concluding that this variable plays an important role or statistically important role in the model. Multiple r square is 64.45%. So that's the contribution that this variable, right now this is simple linear regression where we have only one x variable. So it explains about 64.45% of the total variability in depression. So just by using one variable, we are able to explain about 64% of variability in the model. So the equation, if you see, the model basically has two components in it. One is the explained variability, like why do we see variation? If you look at this scatter plot, we see variation here. And if you ask a question why we see this variation, we can say very safely say about 64% of that variability is because of one variable weight. And then there is the remaining part which is unexplained part, or which is like in statistics, whenever we have something which we cannot explain, so we call it error, or more appropriately we call it statistical error. These values in terms of weight seem very close, like this and this. These 2 points are very close in terms of weight, but in terms of depression you have like a big gap here. So why that gap is, we don't know. So it is unexplained, and in statistical language we call it error. So that's what goes into error. But overall we see that even for the model, p-value is quite small, 0.005. So we can safely say weight has statistically significant impact on depression. But if you include the square term or quadratic term, like y equals intercept plus b1x plus b2x square, so this is the square term that I have added. And although like on the graph it looked as if it is doing better, but statistically there is no proof, because p-value is 0.25. So 1 minus 0.25 is just around 75%. So having 75% confidence in concluding a variable to be significant, or a contributor to be contributing significantly, so in statistics that's not used. We need to have at least 90% confidence or more. So anything less than 90% is not even considered. So although like your R square is going up, I think it was 64.4, it goes up to 70%. But then there's a red flag raised by the p-value, the last column, where it says that it's not really contributing to the model, because the model looks at not only R square but also the variability part, and it considered this to be not statistically significant. So you can see like sometimes just by looking at the graph it may not be enough. We may not be able to judge, and if you give this same picture to 100 different people, so different people may conclude differently. So somebody may look at it and feel that this is useful, another person may say this is useful. But by doing this extra analysis, everybody comes on the same page very quickly. I think somebody also mentioned in the chat room. So a linear model where you are trying to apply nonlinear and making it unnecessarily complex, so that's what in statistics we call overfitting. You are just simply overfitting. Overfitting means that maybe your model is doing slightly better with this data, but if new data points are collected, so your accuracy of your model may not be what you see with the data. Like we can make a very complex model and make this line go through each and every point. So first point, second point, zigzag, and we may come out with a very complex model, but that will be a simple case of overfitting, where it does well only with the data with which it is trained, but with any new data point it will be totally off. So we also look at the diagnostics, because statistical models make a lot of assumptions, and we have to be careful before we start using the model or make any decision. And in R especially, you get these 4 plots that help you to confirm whether assumptions are being met or not, and if there are any red flags. So one of the assumptions is about linearity. and it gives you a plot where residuals are plotted against fitted values. So residual is basically observed, the actual data point minus the predicted data point. So when you take that difference and plot it with the fitted values, you will see in this picture there is a dotted line, very faint dotted line in the middle, and this red line should be close to that dotted line. If the line that you get here is closer to it, that means the assumption of linearity is being met. It is not possible actually with real data to get perfect line on exactly on this dotted line. It will never happen with any real data set. So some fluctuation above and below are bound to happen. But if more or less the pattern is close to the dotted line, that means we are okay as far as linearity is concerned. But if this line was like very away from the dotted line, then there would have been some cause for concern. Another thing we can actually look for here is whether the variability is changing as we go from left to right. So whether there is any obvious pattern that you observe in these data points, or they are randomly distributed across that dotted line. So more or less we can say it is randomly distributed, and it also highlights 3 points here like 5th, 7th and 8th one, which are among the highest or lowest. So those data points are highlighted in this plot. If you need to go back and check if there was any data entry error or any problem, you can check these 3 data points. So it doesn't show that variability is significantly changing as you go from left to right. One of the patterns that highlights that kind of problem is if you see a funnel shaped pattern. So maybe low variability in the beginning and then it keeps on increasing as you go from left to right, or the other way. So that would have indicated that variability is changing, but it looks okay. Another thing is normality. Normality of standardized residuals. When you plot it on a QQ plot, so this is a special plot used for verifying normality, especially when you have small data set, because you have only 10 data points and it's not possible to create a histogram and see nice inverted bell-shaped curve with 10 data points. So this QQ plot is very useful in those situations where your sample size is small. And the way it has been designed is the normal distribution has been actually changed in certain way or transformed in certain way, so that if data is coming from normal distribution, they will plot in a straight line on this QQ plot. And usually we give more weightage to the middle points compared to the data points in the tails. So this also actually highlights 3 extreme points. In this case, 3 points are 7th, 8th and 10th. So 7 and 8 were actually flagged here, and 7 and 8 is flagged here also, and a new data point which is flagged is 10. So those are the points if you need to go back and look at to see whether there are potential outliers in your data or not. The third graph is for scale location, and it also helps to understand homogeneity of variance. So whether there is any obvious pattern that we see with the square root of standardized residuals against fitted values. Another name for homogeneity of variance is whether there is a homoscedasticity. So that's another name which is used. So that's one of the assumptions for using a linear model. The last one tries to highlight any high leverage point in your data set. So a point that has a big impact on the model. So this is a small data set, and there are only 10 data points. But when you have large data points, there is more possibility of errors in the data, and it can help to identify if there is any data point which is having a big impact. And it uses a statistic called Cook's distance, and you may see these dotted lines here. So if there are any data points beyond these on the upper or lower side, so those points are basically high leverage points. They have big impact on the model. So one data point having a high impact obviously may be a cause of concern. So you want to confirm whether that data point is genuine or it has some issues. So in this case, a 10th data point is again flagged as high leverage point. It is just on the borderline actually. It's not very far away, but certainly it is flagged here. So using these four plots, we understand the model and we try to understand whether it is following assumptions or not. With any data, it is definitely something we need to verify by looking at the plots. So these four plots that you get are very useful.
I have a quick question. On the last plot, there was a small portion with the red dotted line in the lower left-hand corner of the high leverage points.
This one?
Yeah. What is that?
Oh, that's just the label for Cook's distance. So it only means that the dotted line is nothing but Cook's distance. So those lines are here. So this is just representing, just saying that dotted line means Cook's distance.
Okay, thank you.
Yeah, this is actually not part of the plot. It could have been like kept outside, but it just says that dotted line means Cook's distance.
Professor, sorry, one quick
Yeah.
question. Why is 8 highlighted in the normal QQ plot? I know 10 and 7, they're far away from the dotted line. Maybe that's why, but what about 8?
In all four plots, the default setting is 3, and it highlights 3 points on the extremes. It doesn't mean there is something wrong in it. It just highlights 3 extreme points. So you see this is extreme on the upper tail, and these two are extreme on the lower tail. So it doesn't mean there's something wrong with it. It's just the default setting.
Okay.
You can make it just 1 or you can make it 5. So that is a default thing.
Just a quick question, Professor Rai. Somebody's asking what is homogeneity, this one on the left-hand side.
So homogeneity, meaning of that is uniformity. Like if you look at the first plot, for example, when you go from left to right and you see the data points are scattered evenly, so that means homogeneity of variance. The variability is more or less not changing significantly. But if you have like something like a funnel shaped pattern, so very little variability in the beginning and then keeps on increasing, so that will be violating assumption of homogeneity of variance. So you can get it from like this plot, you can also get it from this plot if you see any obvious pattern. But right now there's no cause for concern here, so everything looks okay. So you have seen in the previous plot we made use of normal distribution. So normal distribution is a very important distribution in statistical modeling, and it plays a very important role. And another distribution that plays important role you have seen in our regression model where we calculated t values, that comes from t distribution. if you look at these two pictures, one is for normal and other is for t-distribution, you'll notice that they look similar. And in fact, these two distributions are similar. The only major difference is in the tails. So in the tail of normal distribution, if you compare that with tails left or right for t-distribution, you'll find that for t-distribution tails are thicker. But both distributions are symmetric about the mean, and the shape looks more or less similar. If you calculate area to the left of -1, like to the left of this point, so there is a function in R, P norm, P for probability and norm for normal distribution. So simply by using that, you can get the area. So this is like 0.15. About 15.9% of the area is left to the left of -1. But if you do a similar calculation with the PT for t distribution, I have used degrees of freedom as 3 purposefully, like I used a smaller one representing a smaller data set, because that's where t distributions are used when your sample size is small. So if you calculate probability to the left of -1 in this picture, you get 0.196, 19.6%. So you can see from 15.9% it goes up to 19.6%. So that's a big increase for area to the left of -1. And the reason is that in t-distribution tails are thicker. And tails in t-distribution actually start becoming thinner and thinner if your degrees of freedom or sample size increases. To the extent that if your sample size is 100, your t-distribution will start resembling a normal distribution. So R allows us to actually simulate data from these kind of distributions in statistics, and some popular distributions are like normal, t-distribution, uniform, and exponential. Exponential is usually like right skewed. So you can generate random numbers from each of these distributions using just R and then the name of the distribution, like NORM for normal, T for t-distribution, for uniform UNIF, and exponential is EXP. So very easy. And when you are generating random numbers from normal distribution, this number 1000 means I want 1000 data points. So every time you do that, it will generate 1000 random numbers very easily. Later on, I'll also show you how to generate random numbers with a specific mean and standard deviation. So this one, as you can see, it is from actually standard normal distribution. So mean is 0 and sigma is 1. Now these are histograms and QQ plot or normal probability plot side by side. When we have a sample of 1000 simulated from normal distribution, and you can see the pattern is normal, but it can be more easily judged on the probability plot compared to normal distribution. So sometimes you may look at things like more minutely. Somebody may say maybe this tail is thinner and this tail is thicker, something like that. But in probability plot, as I said earlier, we mostly focus on the middle points, and tails, little bit of deviations are expected and they will be there, but this is more or less a normal distribution. Similarly, you can see just by looking at histogram that these random numbers were generated from uniform distribution. So obviously it's not a normal distribution because tails are missing. And how it will be represented on a probability plot. So you can see there is a very significant deviation in the probability plot. So middle points are okay, but very quickly you see a very clear-cut deviation from both upper and lower tail compared to normal distribution. Yeah.
Just quickly interrupt. A question from James saying, when we check normality, we're looking for the normality of the residuals, correct?
So it can depend on the application. So right now I'm showing you like how you can check, but usually sometimes we look for normality of even a variable. Sometimes we are looking at a normality of residuals and some other things, but the method is same. You would still plot a normal probability plot, and on that plot we'll be able to see whether that thing of our interest is normally distributed or not. But it could be for like different applications. And this is how exponential distribution will show up on normal probability plot. So you can see very clearly it deviates from the straight line and it's not a normal distribution. So now I purposefully have generated only 20 data points, and there is no way you can make a histogram and conclude based on the histogram whether the data is coming from normal distribution or not, because sample size is too small. 20 is too small for any clear pattern to emerge on a histogram. But that's where normal probability paper or this QQ plot comes handy, and you can see those data points are hugging the straight line consistently. But this one was generated from random normal distribution, and next one I used clearly exponential distribution, and you can see how there is some kind of curve appearing on the normal probability plot. You can also compare two distributions. Here I am comparing two normal distributions that have different mean. I have generated X where mean is 2 but standard deviation is 5, and Y I have generated 100 random numbers where mean is 6 but standard deviation is same. So on a normal probability plot, those two lines will appear almost parallel. But if you change the standard deviation and keep mean same, you get this kind of pattern. So I have kept mean as 2 for both. First one standard deviation is 5, second one standard deviation is 20. So when you have higher standard deviation, slope of the line becomes steeper, right?
The other way, right? Isn't it spread out over the red line would be standard deviation 20 here?
I have used actually blue color here for the second one, Y. So blue color you can see is steeper. So if slope of that line is higher, that means higher variability. And if the slope is lower, that means low variability. So that's how we can identify different standard deviation on a probability plot. Now related to various distributions and also normal distribution specifically, there is a very popular theorem in statistics. It's called CLT, Central Limit Theorem. I'm trying to show this visually to you. If you take repeated samples, maybe 100,000 data points from a normal distribution and plot a histogram and also a curve, that's going to look normal distribution. So we are not doing anything, we are just taking repeated samples of size 1. Gamma distribution, exponential distribution is basically a special case of gamma, but it's a right skewed distribution. So it is going to retain that shape. Uniform distribution is going to look like this, and beta distribution is more or less like U-shaped. It's going to look the way you see. But if we increase the sample size from 1 to 2, what we are doing is, from a normal distribution, we take a sample of size 2 and find the average, again take sample of size 2, find the average, again take a sample of size 2, find the average, and generate like maybe 1,000 averages. This is going to be the pattern. So it is going to look still like a normal distribution. But gamma distribution, if you are repeating that, you are going to see slight change compared to earlier. Earlier it was very highly right skewed. So now that skewness, just with the sample of size 2 and finding the averages and creating a histogram, that skewness starts to decrease. What happened to uniform distribution? That already starts looking like somewhat, not exactly, but somewhat like a normal distribution. And there is also some churning taking place in beta distribution. It is no more U-shaped, but it looks bimodal by now. So that means data points are coming towards the center.
Just very quickly, Prof. Wright, is this sampling with replacement or no replacement?
With replacement, like you are taking samples with replacement.
Okay, thanks.
Yeah, so you have like as if like infinite data points in a normal distribution, and you can take as much as you want. So this is with size 2, but if I increase my sample to 10, so what I'm doing now, I'm taking 10 samples, finding the average, recording that average, again taking 10 samples, finding the average. So that's my second data point. Again 10, find average, third data point. So now I have another 1,000 data points. So if I'm doing that with normal distribution, no change. Normal will remain normal. But even gamma, that used to be a very highly skewed, right skewed distribution, is beginning to be seen like a, it is, you can see like the picture moving towards normal distribution. Uniform already looks like a normal distribution. Beta also looks like normal distribution. In fact, beta was the strangest one out of 4, and it's already looking like a normal distribution. Same thing with 30. If you have samples of 30 repeated 1,000 times and you plot them, you see everybody looks same now, more or less. Actually, this is central limit theorem. Like when you have sufficient sample size and you create distributions of averages from that, your shape is going to look like a normal distribution. And in statistics, people also say like anything like n sample size greater than or equal to 30 is a large sample. So the reason is this, because many times in many situations, central limit theorem can kick in and help you to simplify your calculations and help with the various assumptions of normality when your sample size is 30 or more. With 100, you can see even the histograms look equal or same. So this is in a nutshell, this is the central limit theorem. So whatever may be your initial distribution of variable x, x may be any type of variable. It can be height, it can be length, income, it can be residuals, it can be square root of residuals, whatever. So whatever may be the shape of your original distribution of x, this is like uniform, right skewed, bimodal, or any type. If you take sufficiently large samples like n greater than or equal to 30 and calculate x bars. So take 30, calculate x bar. Let's say first one is 12 point something, second one repeat 14 point something, and so on. So this distribution at the bottom is not for x, this is for x bar. It is the distribution of averages. So it is going to look like a normal distribution with same mean as the original distribution, but variability is not going to be same. Variability will be sigma. Sigma is the variability of distribution of x. So sigma divided by square root of n. So if n is 30, so it is going to look like this. And this is what we called, like, you can represent this by sigma of x bar just to differentiate, like this is not for x but for x bar. So sigma of x bar is called standard error, not standard deviation, because sigma is standard deviation, but sigma of x bar is standard error. So more formally, central limit theorem is defined as if a variable x, which can be anything, any variable on earth, has unknown distribution with mean mu and standard deviation sigma, then sampling distribution of x bar, actually this bar has moved here, so this should be x bar for mean, having a sample of size n will have same mean, so mu of x bar will be mu. Standard deviation will be actually standard error, where sigma divided by square root of n, tend to be normal as the sample size becomes large. So in statistics, large means more than 30. And this is for unknown distributions. If your original distribution is normal, then even with the sample of size 1, it's normal. We have seen that. And another thing that happens is when n increases, you can see the standard error has n in the denominator. So when the value of denominator goes up, when the sample size increases, the distribution becomes narrower and narrower. So variability or the standard error reduces because n is in the denominator. So that distribution becomes narrower and narrower. So one example here from bank. A bank has kept records of checking balances of its customers, and they find that average daily balance is $300 with a standard deviation of $48. So this is, people don't keep much in checking anyway, because rates are so low, and by having money in checking account, you're not getting any interest. So even if you keep $300, I don't know, maybe you get 1 cent in a month. So a random sample of 144 checking accounts is selected. So obviously bank has to make some strategies of managing this money. So what is the probability that the sample mean will be less than 306.6? So one thing you'll notice is when someone is asking this question, they are not asking about one customer. So as a bank, you're not like worried about like one customer having like $306.60, but you look at the average, and that's why it says sample mean. So whenever these kind of questions you try to answer, you have to remember that when we are talking about sample mean, and especially sample size is now 144, much higher than 30. So you don't have to assume anything now. You don't have to assume that the original distribution has to be normal. Nowhere in the first paragraph it says it is coming from a normal distribution, because that assumption is no more needed, and that assumption is no more needed because of this central limit theorem. So central limit theorem says that if your sample size is more than 30, forget about everything, like whatever may be the initial distribution, that unknown distribution doesn't matter, you are using normal distribution. So this way, normal distribution can be used in combination with central limit theorem. There is a interesting paradox you may come across, or you may have heard of, Simpson's paradox. And it is important to realize that these things can happen when you look at any data or summary of data, so that you are on guard, you are cautious while making any conclusion. So this data was from University of California, Berkeley, student admissions data, and aggregate data on applicants to graduate school. So those people who are applying for 6 largest departments. So this is old data, 1973. And you have this summary now. Male 2691 applied and 44.5 were admitted. Female 1835 applied, 30.4% admitted. So although like number of female applicants was slightly small, but in terms of numbers, it's not a small sample. We have 2600 or about 2700, and here also more than 1800. So we have a lot of data, and you calculate this percentage, it comes to 44.5 and 30.5. So there were some people who accused this university of bias in admissions by saying that just looking at this table, sometimes we can conclude, so males are about twice as likely to be admitted compared to female. So there's a odds ratio of 2:1. And this is a plot you can see. So this is admitted, so more male students admitted, and here you can see more female students rejected. So if you look at the next plot, so similar plot, but now it is department wise. As noted in the previous slide, there are 6 departments. So when you look closely, so first department, the bigger blocks are for green, which is for male. Clearly, a lot of students apply to graduate school in department A, and a lot of those students are male. So female students are not applying mainly to department A. Female students are applying more to department C and maybe department E, and about 50-50 in D and F. So department A and B is very popular with male students, and almost everybody who is applying here, they are male students. So this Simpson's paradox basically highlights the problem with this conclusion here by just looking at the overall rates and ignoring what's happening inside. So inside you can see the dynamics are very different. It's not like 50-50 everywhere. And females apply more to departments with higher rejection rate. So that's what was going on. They were applying to department C where rejection rate was like historically very high. Another example is a hospital success rate. If the question somebody is trying to answer is, which treatment would you prefer for your kidney stone? Treatment A or treatment B? Just by looking at the numbers, we see that treatment B has 83% success rate. And someone who is not careful and who doesn't ask deeper questions may be misled into concluding that treatment B is better than A. But if you look at the breakup, so small stone, treatment B actually has a much bigger sample, 270 versus only 87, and vice versa for treatment A. And like large stone, you have 263 versus only 80 for treatment B. And when you calculate the percentage, it becomes even more like skewed. So 93%, 87% treatment A wins, 73%, 69% still treatment A wins. But overall, you had a higher percentage for treatment B. So this is also example of Simpson's paradox. So size of the stone is the confounding variable, also known as lurking or hidden variable. So sometimes there may be some variables playing a role. If we ignore, we may conclude inaccurately, or we may take decisions which may not be correct. So it highlights importance of understanding the data and its limitations. Simpson's paradox may exist if we do not stratify data deeply. So it is always advisable to stratify your data. Too much aggregation can introduce bias. And Simpson's paradox can be avoided with the help of tabular or graphical summary, like the picture that I showed you was able to highlight things very clearly. So with the help of tabular or graphical summary along with a thorough understanding of the problem being studied. So we have to be careful in statistical modeling when we have these kind of situations. So today we'll use RStudio Cloud. I got you started with R in Kaggle notebook, but RStudio Cloud provides few more features that you'll find are very useful. It is going to take you to this page if you already created account. So initially you'll see this is empty. If you want to create a new project, simply click. It will open up this window here, and we can give a name at the top. So let me call this week 3. So when you open, you'll see there are 3 windows. This is a console window. This is where you'll get the outputs. For example, if you do 5 plus 5, hit enter, you get 10, or whatever code you run here, you immediately get the output. But if you click on this corner, it will open up a new window. So if it was like this and you click here, this window pops up where you can type your code. Or another way is you click on this plus sign and say R script. So that also opens up a window. But then you already had untitled one, now it creates another one. So I'm going to keep just one. At the top under tools, if you go to global options, you can customize the field and the look of it. So for example, under appearance, instead of 10, I'm going to use maybe 18 so that it is slightly bigger and you can see more clearly. But you can make any change you like here. So default is text mate, but if you like maybe dark or whatever the other format, you have so many different options. So tomorrow, tomorrow night, 80s, blue, bright, twilight, so a lot of options. Basically in the background, this RStudio Cloud is using R, but R doesn't have a very user-friendly framework, so that's why different people have come out with different options. Like Kaggle notebook was one that we saw, and RStudio is very popular. There is a desktop version, but the one we are going to use is RStudio Cloud, and the advantage is we don't need to download or install R or RStudio. We can just get started. We type the codes here and use run button to run the codes. I will show you that, and you get the output here, just like what we did earlier, 5 plus maybe 7, and you click run, you get the answer in console area. To run this line, there are various ways. You can be anywhere in the line. It doesn't matter whether you are before 5 or in between 5 and 7, and click run, you get the output. Another way is you select everything and then click run. That also will lead to same thing. Or if you are anywhere in the line and if you like keyboard more than mouse, then control enter will also run the code for you. So I'm going to start with some libraries. And one of the libraries that we have been using is DAAG. So one thing you'll now notice is as you type, it gives you various options immediately. So you don't have to complete, you can just go and select the one that you want and it will accept that. So we say DAAG. Now if you run this line, you get an error that there is no such package called DAAG. And that package is not there because we have not installed it. So one extra thing that we have to do in RStudio is any package we are going to use for the first time, we have to install. So I'll show you how to install. It's very simple. If you look at the fourth window, it has files, plots, packages. So if you click on packages, you will see there is an option called install. So I'm in the fourth window and I clicked on packages and then click install, and then you type the name of the package that you want and use the default whatever settings you have and click install. It will take few seconds and install the package for you. You may not see something happening immediately. You wait for a few seconds and then it gets going. So while it is installing the package, let me also tell you, in the console area there is a stop button. So when R is doing something, let it first complete before you try to run something else. So when you see a stop button, just keep patience for a few seconds and let it complete its task, and then it will go away. So that stop sign has gone away. Now the package has been downloaded. So it gives you a lot of output while doing it. You can ignore everything and come back to line number 2 and then try to run this. So now it says loading and it's done. Another package that we'll use and we have used is ggplot2. And again, because you are using this for the first time, we'll have to go to packages, click install and type ggplot2 and then click install. So this is a one-time extra activity that we have to do that we did not have to do with Kaggle notebook. But now since you are familiar with the basics, so we can work with RStudio because it has more interesting features. So ggplot2 may take slightly more extra seconds compared to the first one because it's a bigger package. And once it is done, run the library line ggplot2 to activate it, because unless you run the library line, that package will not be active and you cannot use its functions. So I showed you roller data from DAAG package in my PowerPoint. So if you do structure, if you want to look at the structure, it has 10 observations. There are 2 variables, weight and depression. So this is the data that we had used. I'm going to make a scatter plot. So we have been using ggplot function for scatter plot, and our data is roller. So I'm making a scatter plot between weight and depression, where weight should go on x-axis and depression on y-axis. And that we do by specifying aesthetics. So in aesthetics, on x-axis we say VEIGHT for weight, and on y-axis we want depression. And then we add a layer GEOM underscore point for a scatter plot. And when you run that, your 4th window becomes the place where you can see the scatter plot. So because it has files, plots, packages, help, etc. So whenever you make a plot, that will show up here. And you can export these pictures very easily by clicking on export. You can save it as an image. If you are writing a project or working on a paper, research paper, if you want high quality graphics, you can save it as an image or save it as a PDF. Or if you do not like the dimensions, click on copy to clipboard and you can change width and height as you like. So usually for scatter plot, you want to have a square pattern. You don't want a rectangular pattern, but square pattern.
Possible to show the students how to knit the entire our code with a graph and also the result. Somebody's asking if you know how to put our code with the graph and the results by knitting.
Yeah, I'm going to show that. Yeah. Okay, so you saw like 4th window in action. In the 3rd window, we have like environment, history. If you click on history, whatever we have run, it gets accumulated there. From time to time, if you have been doing some exploratory kind of analysis and you have done a lot of things, it may be a good idea to clean up things. So for example, you have this brush here, broom. If you click there, it will simply clean all the entries. Same thing for console. If you have a lot of stuff there and you want to start with a clean slate, if you do Control plus L, so Control starts with C and L, so clean. So it will clean up everything, or you can use this brush to clean up things. I have not done much, but if you look at the code file name, it's called Untitled. But if you go to File and click on Save As, you can give your own name that you like. So for example, if I say BK1 I'm just using some random name, and click save, the name of the file changes to bk1.r. So any R code file gets automatically saved as a .r file in RStudio or in R. If you go to the fourth window and click on files, you will now see, apart from like whatever default files you had there, now bk1.r that we just now created also is listed. So it gets listed under your project folder. So we made this plot. You can always drag them and increase, decrease to make more room. But in the next line, I want to do a linear model, and I will save that linear model in model by pointing an arrow towards it. And for linear model, the function is lm, and then we can say like y as a function of x variable, y variable as a function of x. So first we put y variable. In this case, it is depression. And then you put a tilde sign, the symbol below escape button, and wait. Because we only have one variable. If I run this structure, you will see this data has only one independent variable, wait. And our data set is called roller. So we can run this and then type summary of our model and get the summary that you saw in the PowerPoint. So it gives us like more information like residuals, what is the minimum, what is the maximum, and first, third quartile and medians, but mainly intercept and slope, and you have seen the p-values, r square, and so on. This model object contains a lot of information actually, and if you do names model, it will tell you what all things are included here. In the model you have coefficients, you have residuals, effects, rank, and so on. So a lot of different values are available in model. So for example, if you want to look at coefficients only, COEF, you can use the short form or the complete coefficients, anything will do. And model, so instead of like entire summary, it will simply tell you intercept is this and slope is this. If you want to look at residuals, you can do the same thing. For all 10 data points, it gives you the residual values. Residual is nothing but error. So residual is observed value minus the predicted value. Let me show you one calculation. Roller, first row and all columns. So first weight value is 1.9 in the data set and depression value is 2. And then if we do, what was the name for fitted values? So fitted dot values. So these are fitted values. So observed value for the first one is 2. So 2 minus this fitted value 2.9, etc. I'm going to paste it. So observed minus fitted value is negative 0.97, etc. And that's exactly the value that you have here. So that error is basically observed minus fitted value. Now let me go back and include this model, linear model. I'm going to add a layer in scatter plot. So we had earlier used this smooth, where we can say method equals linear lm. And while I'm here, I'm also going to give a title. And probably a subtitle also. Something like this. And you get this straight line linear model and also 95% confidence interval. Okay, so I'm going to save this file by clicking option to save here. And what we'll do is you can click on file and say new file. Under new file, go to the third item. It's called R Markdown. RStudio helps you to create various types of files. R notebook, you can create shiny web apps and many others, but go on the third one, R Markdown, click there. So when you click there, it says creating R Markdown documents require updated versions of following packages. So it gives a list, and then it will ask you a question whether you want to install. Say yes, and then give it like few seconds. And then it will do few things and make everything ready for you. Okay, so now we have a R file open. I'm also creating another file just to illustrate how you can convert your work into a PDF or a Word or HTML. So this is how you do it. You can give the name, any title that you like. So let me call this week 3. And let's say I'm the author. And then there are various options, HTML, PDF, Word, etc. So right now I'm going to choose Word, because let's say you do some work and create a automated Word file from RStudio, and then you want to add maybe comments or whatever you like, you can do that and then change it to PDF. So let's say I want to do that. So it immediately creates this template. This is an empty template. There's nothing here right now except few standard things. Let's get rid of this whole part. And I'm going to leave these as it is at the top. Although I can, if you like to change anything, you can easily change here, but I'm going to leave it as it is. And then you will notice in line 8, there is a chunk. So this block or chunk, it starts with these 3 symbols and ends with these 3 symbols, and then in between you may have some codes. So instead of like typing those symbols and trying to find where it is, there is a shortcut where you can say, I'm using Mac. On Mac, it's Command Option I. Command plus Option plus I. Anybody using Windows, can you tell what is the shortcut?
It's Control Alt I.
Okay, so on a Windows, it should be Control plus Alt plus I. On Mac, it's Command, because there's no Alt on a Mac keyboard. So it will create an empty chunk for you. And what we can do is, because we have already run these things, I'm going to copy, let's say, this part into this chunk. And if you click on run, you see this green play button. If you click on that, any output will be just below this chunk. And after that, I'm going to add another chunk, Control Alt I on Windows, Command Option I on a Mac, and I will copy and paste the whole scatter plot thing. If you run, you immediately get the plot below your code, just like what you saw in Kaggle notebooks. The third and last chunk that I will use here, and I'm going to only use lines 14, 15 and 16 here, just to ensure there is only one output. So we run this, and immediately below that you have the output. So that means whatever chunks we have added, everything is working because we have already run without any error. So now what we can do is we have to name this file. This markdown file is named as Untitled 1. So if we go and say save as, let me use week 3 itself. So it gets saved as week-3.rmd, R markdown file. It has a different suffix .rmd. In the first window, there is a knit button, but click on the drop down, this small arrow pointing downwards, where it will give you various options like whether you want to knit this as HTML, PDF, or you want to knit Word. Now for Word file, to enable you to open on your computer, obviously you need to have Microsoft Word. So I'm going to use a knit to Word and wait for a few seconds. So R Markdown has finished rendering this download file. So I'm saying yes. Open with Word. I'm saying yes. So this is how it looks. You saw at the top we had the title week 3, my name and date. And then you have code, output, plot, linear model, summary. And once it is in Word, if you want to add anything here, or if you want to add directly somewhere on your markdown file, you can do that. I'm going to cross this RMD file, and I'll continue to work in R file. Another thing is when you go to your folder, files folder, so now you'll see that your week-3 RMD file, R markdown file is there, and also your Word file that we created, week3 docx. It's sitting in the cloud, and if you need to download, you can select, and if you click more, drop down more, you have option to export. So you can download to your computer and do whatever you like to do. That was like how do you create markdown file. So let me continue with what we were doing. So we created a linear model, and remember I showed you 4 plots. If you want to have 2 rows and 2 column plots, there's a function called PAR, and then MF row equals, and C within parenthesis 2 comma 2. So 2 means 2 rows and 2 columns. So that means if I run this line here, after that any plot that I plot, it will try to have 4 plots together. So let's plot the model that we created by using plot model, and you immediately get these plots that we had. This is exactly same plot that I used. When we make a model, sometimes we have to do predictions, and you can predict using predict function. We have to specify what is our model named as. So we remember we named our model as model. So that, and then what do you want to predict? So that we have to say what we want to predict. We can say, let's say I'm just making up something, data frame where weight, because weight is the independent variable, so we want to make predictions for different values of weight. So if you want to make predictions for, let's say, weight equals 7, if you run this, it says if the weight is 7, then depression is likely to be 16.58. So that's a prediction. So it's a point estimate. It's a single point. It's a single point estimate without any confidence intervals. If you have more than one number, for example, this is the format we use. For more than one numbers, we put C, and within parentheses, we can say we want when weight is 7, when weight is maybe 8, and when weight is 9. So we want predictions for these three values of weight. So it will give you predictions of those three values. So basically it's using that straight line and putting the value of weight and giving you the output. But you can also use this further. So let me go to just before data and hit enter to make it cleaner. So I'm going to add third item within the predict, where we can specify interval. So there are two types of intervals that generally people use. One is called confidence interval and other one is called prediction interval. So if I put within quotes confidence and run this, so it will give me these predictions like same 16.58, 19.2, 21.9. Those point estimates are the same numbers below fit, but then you have a lower and upper bound of that confidence interval, and by default it is 95. In statistics, anytime, anywhere, if nothing has been said about confidence, people assume 95%. So 95% is the most commonly used confidence level, and it tells you that you have a confidence interval of 95%. So this is the lower and this is upper.
Prof. Rai, just very quickly, how do you read the third plot in the model, the scale location? What does that tell us? The student is asking.
Homogeneity of variance. In the PowerPoint also I mentioned one of the assumptions is that the variance doesn't change when we go from left to right or right to left. So it is to verify whether we have the statistical term that we use is homoscedasticity. So it's a name given for homogeneity of variance, like uniformity of variance. So variability doesn't change when the values of, let's say, weight or the fitted values increase or decrease. So that's what it means. Now, what does a confidence interval mean? So as per the model or simple linear regression model that we have created, as per the model, when the weight is 7, when the weight of the roller is 7, depression is likely to be between 11.4 and 21.7 on an average. So the key term when I'm explaining this confidence interval is on an average. On an average, the values are likely to be between these two numbers. So when we talk about confidence, we talk about the values on an average. But I can actually copy this whole thing and paste it again and change from confidence to prediction interval. So there's something called PIs, or prediction interval, and you'll be surprised when you run this and when you compare. So point estimates are same. Point estimate for the three weight values are exactly same, but you will notice that the interval for prediction is much wider and interval for confidence is much narrower. So confidence intervals are narrower because the focus is on average. So average values don't change much, but individual values change a lot. So how do you do interpretation of prediction interval? If you consider the first one, if the weight is 7, depression is likely to be between 0.22 and 32.9 for a roller on basically 95% prediction interval basis. So it is for a single value. This prediction interval is for single value, but confidence interval are for averages, and that's why you see the big difference. So that's why sometimes confidence interval is called narrow interval and prediction interval is called wide interval. Somebody may ask, like, which one to use? Should I use confidence interval or should I use prediction interval? The one you are going to use will depend on what is the context. I gave you one example of that bank where somebody was interested in, on an average, what are the chances that the balance will be less than $306 or something. So the question was in terms of average. But if the context is individual prediction, so there obviously confidence interval should not be used. We should use prediction interval. If the context is about a single value, we should use prediction. But if the context is about average of something, we should use confidence interval in those cases. If you use vice versa, like if you really need, the context is about a single value, and if you use a confidence interval, so then you are going to very greatly underestimate the variability expected, and you may have like misleading conclusions, and what you conclude and what you observe may not match. So which one you should use depends on what context it is being used for. What is the business question? I'm going to go up and copy this scatter plot part. So let's do one thing. We'll do predict and we'll do the model, and let's do interval equals prediction and save this in P. One thing you'll notice is when you run something and you get a warning message, warning messages are okay. So it's like when you are driving on a freeway and you cross the speed limit and the police comes and gives you a warning, you should be happy. You are still not getting a ticket. You get a ticket when you have an error message. So in R, if you get an error message, there is a problem. Warning messages, you should be happy. It's okay. It's just for information. You want to read it, or just ignore it. So I'm going to ignore this. I'm going to add one more line where I will create my own data, and this data will be a combination of roller data and the values stored in P. Remember, P has fit values, lower and upper prediction intervals. So I want to combine actually columns. So the way you do is a C bind, column bind, first one. So first we'll put roller and then we'll put P and hit run. If you want to look at str data in your console area, you'll see that apart from weight and depression, now you have fit, lower and upper values. because I want to plot that on the scatter plot itself. So instead of roller, this becomes data. I'm going to add a few things. If I just run this part, these are confidence intervals automatically from ggplot, but I can also include the prediction intervals which are like wider by using GEOM underscore line, where we can say aesthetics. So obviously it is with respect to Y values, and LWR for lower and upper is UPR. LWR. We can also say color, we can make it red, and line type we can say dash, just to keep it separate. So you see it adds the lower, and if I do the same thing plus, copy this, and instead of lower, if you do upper, this is what you can add prediction lines on the same plot. If you want to make these lines thicker for whatever reason, you can add line width WD, LWD, let's say 2 times, it makes it thicker. I also showed you quadratic term. Let's say we call it new model, model 1. Again, linear model, depression as a function of weight, but we also want to include plus, and the way we include quadratic term is I within parenthesis weight square, and then obviously we have to put comma and mention what is our data. So if you run that and do summary of that model 1, you can see the square term gets added, and I also showed you it is not statistically significant, so it doesn't help, but this shows you how you can do that. Just a second. Yeah, at some place, actually line number 21, I made this format 2 by 2 when plotting the model. So usually it's a good idea to end that with the dev dot off, this first one, and run that so that it will not affect future plots. Okay, anyway, so central limit theorem will need a library teaching demos. Click on packages, click install. RStudio Cloud is smart. So you can see when I type this, and before I was like looking to install it, it automatically at the top in yellow line it says this package is required but not installed. Do you want to install? So simply click. So that's another way you can install a package.
Just very quickly, Prof. Rai, there's a question on the graph you showed earlier where you showed the confidence interval. Towards the middle of the graph, it narrows. The question is, why is that narrowing?
Yeah, usually in confidence intervals, you have more confidence in the middle values, and when you start to get towards the outside range, so typically people will not suggest that you use this plot for any kind of predictions beyond the data points. That's never a good idea. This is not a forecasting tool. So the way the model has been built, it cannot be used for like either going on the lower side or higher side. Like I should not use this model to make a prediction for, let's say, 14. So weight equals 14 or 15 because it's not in the range. And as you start to go towards the higher or lower values like extremes, your uncertainty starts to increase. So that typically happens, and we should stop right there. The model should be used for prediction, not in the sense of like forecasting, but predicting a value within the range of independent variables. The idea is like towards the extremes, the variability starts to increase. And we don't know beyond that, so we should not even try. Let me see if it installed. Yeah, so looks like it installed without telling us anything. So the function that we used, or what I used, is called clt.add exam. So if you select that and if you type 1 and run, you get it just with 1, what is the shape, and when you do 10, you can see it starts to become normal, and with 30 everything becomes normal. Last thing and then we'll stop. For normality, so let's say, so this is the code I showed you earlier, random R and then NORM. So let's say I have 1000 values simulated from normal distribution, and then we can use QQ function to plot that. So you get normal probability plot. If you want to add a line, the function is called QQLine. When you run that, it will automatically add a line for you. For any reason you want to have a different color of the line, you can change the color. So with that, I'm going to stop. Any specific question, unanswered question?
Just very quickly, going forward, are we going to use this RStudio Cloud instead of Kaggle?
Yeah, so I'll be using RStudio Cloud. The idea was like, instead of straight away starting here, where you have to install few things and R Markdown, in the past we have seen some students struggle. So instead of starting with something where people struggle, we try to keep it simple with Kaggle notebooks where you don't worry about installing anything, just run the libraries. But now since I see most of you are getting comfortable, I think this will be a good way to get deeper into it, because when you are working on, I don't know, in future if you are working on research paper or some heavy duty project, you will find that RStudio is much more easier. The idea is from that Kaggle notebook to RStudio Cloud, and ultimately at some point I will let you make that decision to RStudio on your desktop, because this one has a lot of limitations. Only I think 1 GB RAM and things like that, and many other restrictions, but you can always use it on your desktop, and then it is limited only by the capacity of your computer. One thing is there, like at some point, like those people who are going to do any advanced thing, for example, running a very complex deep learning model, which will be difficult to run on this RStudio Cloud, and even if you have a 16 GB computer, it may be a bit slow. So that's where Kaggle notebook can be handy. You can convert CPU to GPU using that accelerator and use like the freely available GPU resource and run your models very quickly, because sometimes deep learning models may take like 5 hours, 6 hours on a 16 GB CPU, whereas on GPU you can complete that in much less time. So it's good to know various options, but for me, like I mostly use RStudio for my research and also like related work. Any other question, Darwin?
I think that's it.
I have one question.
Yeah.
So why can't you? It's the save button on this R script is not like highlighted, so you can't click it. Why is that?
Oh, because I already saved. Now let's say I go to the end and I just type the end. So now it gets highlighted, right? So when you add something, it becomes active. But if I click, that means everything that I have added has been saved. There's nothing new. So that's why it is hidden.
Okay.
Okay. With that, I'm going to stop, and I will see you next week.
Thank you.